It's conditional.
No, what you did wrong was.
Okay, let's get started, people.
I think it'll be fun at public service. Isn't that your eye?
All right, so today we'll talk about the topic 3, the trigonometry and the geometry. There are a lot of formula to cover and also quite a lot of content. So let's get into it right away. As always, we'll divide this into multiple sections. And I'm gonna get it slowly. The first part to talk about is the trigonometric, the ratios, and the laws or the rules. And then we'll talk about the radian and the circle. And then we'll talk about the identity. And then we'll talk about the trig functions. And then we'll talk about the equations. And then we have the vector operations. And then we have the equations of lines and planes. And lastly, we have the interactions of lines and planes. Okay, so we have 5 parts of trigonometry and the 3 parts of vector geometry. Okay, so let's start with the trigonometry, the easy stuff. So, the trigonometric ratio and rules. Keep writing reaction. So first of all, we have obviously we have the SOHCAHTOA, and then we also have to talk about the reciprocal ratios, right? So we have the secant, and then the cosecant. Let's use the abbreviation shown in the book, in the data booklet, the formula booklet. Secant, and then we also have the cosecant, and then we have the cotangent. The secant, as you know, we don't have to know the trick, right? We have the formula booklet. Yeah, sorry. The secant is 1 over cosine. Cosecant is 1 over sine, and then cotangent is 1 over tangent. All right, those are pretty easy to use. Let's talk about the rules as well. We have the sine rule and the cosine rule, right? So we can use the trig ratios. These are all for the right triangles, right? And the sine rule and the cosine rule, on the other hand, they're for the non-right triangles. So if you encounter different various shapes of triangles, that's when we use these. Okay, it's Friday afternoon. Triangles. You can use the sine rule and the cosine rule, right? One easy differentiation between the sine rule and the cosine rule is that they take different ingredients, right? So what I like to do is I like to analyze the triangle. When I have a triangle, I like to analyze it into information or a visual. What is it called? I don't know. No. All right. Grouping, or I don't know, visual representation of the question using this diagram of table of values. And then you can use the sine rule only if you have a complete pair, right? So I say this, the sine rule is for a complete pair. So if you have information about the A and the angle of A and then the length B, then this is a sine. Because we have a complete pair here, then we can use a sine rule, right? On the other hand, the cosine rule is when you don't have that. For example, let's say you have the information about the length, the 3 length, then we don't have a complete pair, right? So then we have to use the cosine rule. We cannot use the sine rule. We can also do this if you have the information about the two sides and the angle. Another sign that we can use is cosine rule here. Although we don't have the complete pair, we can still use the cosine rule. So cosine rule is for no pairs. I think this is the easiest way for me to understand when to use which. We also have to talk about the ambiguous case of the sine rule. Right? So basically, the ambiguous case of the sine rule happens because we don't have a diagram, and also because a triangle can have two possibilities of whether it's going to be an acute triangle or a obtuse triangle, right? Okay. So basically, let's say we have a question that uses the sine rule, and then we get the angle C is, let's say, 20 degrees, for example. After we get the angle of 20 degrees, that the second angle to be 20 degrees, we're not done yet, because in the middle of solving the sine rule question, you inevitably solve some kind of problem where sine C is equal to something, right? And when you try to solve this question, sine C is equal to something, we need to know that angle C could either be acute or obtuse, because according to our diagram of all students take calculus, a sine is positive for both first quadrant and the second quadrant, right? Which means that in the first quadrant, my angle is acute, and in the second quadrant, my angle is obtuse. So the result that I get, the angle is 20 degrees. That's one of the possibilities, but it also implies that the angle of 160 degrees, the 180 minus 20, is also possible. So we have to consider the 180 minus the 20, the 160 degrees. And we need to see if that answer is viable or not, right? Ambiguous case does not imply that it's always true. It does not imply that it's always two possibilities. It could be one possibility, or it could be also zero possibility, depending on the sine value that you get, right? So how do you know that? After you find the angle, let's say 20 degrees, and then we have to think about the other one, the 180 minus that, and then check the obtuse one. The other angle that you know. Sometimes that sum, if you add the obtuse angle and the angle that you know from the question, when you add them together, sometimes it's going to exceed 180. Then that's a sign that obtuse angle one is not a viable option, so therefore there's only one answer. If you have less than 180, that means that it is possible, so you can include that two answers. Or in the first place, if you try to solve that equation, sine C is equal to something, and then usually you'll see a question where sine C is equal to, let's say, 1.5, let's say, then it's not possible because sine C has a range of -1 to 1. So that's how the sine rule can have an ambiguous case of either having 0 solutions, 1 solution, or 2 solutions. Okay. One thing to note for the ambiguous case, in your work, you have to reason, to explain your reasoning of accepting or denying the other angle. Okay. So it's not enough just to say, even if there's actually just one answer, if you just say one answer and that's it, then you're going to lose the reasoning points, right? You have to go through the process of checking the other angle and showing that it is greater than 180 degrees. That's why it's not working. Does it make sense? I've seen this mistake on a lot of people's work, so make sure you have that in mind. Basically, why is there an ambiguous case? Because we're doing the sign of it. Sine equals to something. We don't have the ambiguous case of the cosine rule, because cosine is only positive for the first quadrant and the fourth quadrant. And the fourth quadrant, obviously, doesn't make sense on a triangle. Right? All right, I think that's about it for the ratios and and then we have to talk about the applications. Let's talk about the elevation and depression. Elevation and depression is basically when you have the angle of going upwards, that's elevation. If you're looking downwards, that's depression.
Why do we need to know?
Not really. Let's move on. We have to know the bearing though. Okay. The bearing, what is the bearing? Bearing is a way to explain the location of an object from your perspective. So let's say we have a point B here, and let's say we have a point A here. Then we say the bearing of B from A. We use a vocabulary like that, bearing of B from A. And how do you measure that? So imagine you're standing at A, and then you first look towards your north. Right? And then you're going to turn clockwise until you see B. Let's say that angle's theta, or actually let's use an example. Let's say that angle is something like 300 degrees. Then we say that the bearing of B from A is 300. Okay. Usually you have a question that involves the bearing is given, and then you have to make the triangle or non-right triangle in the blank piece of paper. So that's how it's used. And then we have so one tip to give when we're doing the trigonometry or triangle question, if you ever see them, is that we need to have the ability to find the right triangles in a random place, right? Right triangles are mostly useful, but if you have the non-right triangle, that's also fine. But you need to construct that triangle, that invisible triangle, and then it suddenly becomes the sides, side lengths, and the angle question. Okay. Any questions about the trig ratios and rates? The rules? Right, let's move on to the second part. Now we have the radian and circle. So once again, the radian is a SI unit of angle. So by default, angle is measured in radians. Right? So unless a question already tells you that the angle is 40 degrees, you have to always give the angle as radians, right? What is the definition of radians? I think it's the easiest way to understand is that 360 degrees is the full turn, right? The full rotation. And in radian, the full rotation or full turn is 2 pi. Coming from the idea that a circle has a circumference, a unit circle has a circumference of 2 pi, right? Circle is a full rotation, so that's why we have the radian measurement. Okay. One thing to note about the circle is that a unit circle has the coordinates x and y are given as cosine of theta and sine of theta. So this is useful because instead of using two variables, x and y, we can only utilize one variable, the angle, cosine theta and sine theta. We also know that the radius is given as 1, and the center is given as 0, 0, the origin. Okay. Speaking of the circles, we also have the idea of the sector and arc length. I think it's important to just point out that the formula only works for radians. It is written in your formal booklet, but I think quite sometimes people forget about it. Okay. The length of an arc and the area of a sector, the angle is measured in radians only, so it will not work for degrees. Okay. speaking of the formula for the sector and the arc length, I think one part that that left out in this review set is the measurement stuff, or the volume and the surface area and things like that. Although I think that the chance of seeing those weird shapes is quite slim. If you ever encounter them, know that we have the formula for any weird shapes, the volume of right pyramids, the cones, and the surface area of a cone, surface area of a sphere, the volume of a sphere, and such. We all have that in the formula booklet, so hopefully you can find them without difficulty. If you don't find them, you can also check the prior learning part that also has information about the various shapes and the volume and the surface area. Also, ever in case if you forget the area of a circle or circumference of a circle, it's also available.
Well,
Failing at that point.
Don't be in this class.
Your voice was just heard through live YouTube channels, so you may be cancelled for saying that. Oh yeah, also looking at the formula, I forgot about the area of a triangle. In total, after finishing topic 3, we have 3 ways of calculating the area of a triangle. Right? We have the area of a triangle as half of base times height, and then we also have the area of a triangle as half of AB sine C, using 2 sides and an angle between them. And then finally, we have the area of a triangle as, we'll see later, but half of the area of a parallelogram. So it doesn't say it, but we can think about it. The area of a parallelogram is weird shape, and then half of that is a triangle. Okay, we'll talk more about that later. But yeah, I think that's it for the radian and circle. So I think we can move on. Let's move on to identity. So in the formula booklet, we have a lot of identities about the trigonometry, right? Important thing to note is that, like, why do we have them and where do we use them? Right? So identity is useful for many things, but one of them, the most obvious one, is to solve equations. Right? Quite often we need to use our trig identities to swap and rearrange or factor expressions, so we can easily solve equations by reducing the number of variables or simplifying the inside the sine of x, so you don't have stuff like sine of 3x or sine of 4x kind of thing, because the life gets a bit more difficult using those. Or maybe you have like sine of 2x plus sine of x is equal to 0 or something like that. Right? Then we need to make sure that all the sine of x become just sine of x, not sine of weird things. Okay. Although also sometimes the question will kind of guide you through which identity to use, like show that this is that, and then you use that to solve the equations in the later parts. So even if you don't know how to use an identity to solve equations, you still have some other ways, or the question will kind of guide you through them. In the formula booklet, we have number of trig identities. We start with the Pythagorean identity, which goes from the idea of using x squared plus y squared equals c squared, or r squared. We also have the double angle identity. For the double angle identity, the sine 2 theta is fine. With cosine 2 theta, we have 3 different versions of it. So it depends on what question you see and what terms, whether you want, if you only have cosine or cosine squared, maybe you want to use that one. Or if you have both, then we can use the cosine squared minus sine squared. It depends on your choice. Right? So try to plug in different versions of the cosine 2 theta to find the answer. Another instance of using these is that when they're rearranged. For example, let's say you have something like just sine squared theta. Then you can actually go back to rearranging this. So for example, sine squared theta can be represented as cosine 2 theta minus 1 divided by negative 2. Right? So rearrangements of these double angle identities is quite helpful. We also have the compound angle identities, also useful for simplifying some certain questions or problems. So for example, let's say you have a sine of 20 plus x or something like that, then we can rearrange the question in our own taste. The second way to use the identity is to prove another identity. Usually use the proof by deduction, usually. When you're proving another identity, you're going to use some elementary identities usually, right? The double angles, or the compound angle stuff. So this one you just have to practice a lot of trig identity questions.
When
Yeah.
we prove stuff, should we like write the identity itself down as another step as well to show that we are using this identity to move to the next step, or should we just continue with it?
I think it's not a bad idea to annotate some like if you use a double angle identity, just be like, oh hey, double angle identity here.
On like when you do calculus questions, there's many times where they use an identity that's like 1/2 minus 1/2 sine c, and they just use it straight away. Are we just like supposed to know that identity, or like do we have to prove it every single time we use it?
I don't think you have to prove the identity when you use them. If they're in the formula booklet, you can.
They're
just
not
use
in the
them.
formula, but that's the thing.
And if they're like just few steps away, I think it's fine. If you have to use a complex identity to solve, then I think the for those you have to. But I think you wouldn't have that much of a difficult question.
Okay.
Like that level, like that's kind of a weird level of difficulty. It's not just like, yeah.
How would you solve the questions when it's like sine 3 theta or something?
Sine 3 theta. I can think of it right now. And if you have sine 3 theta,
Theta plus
yeah, we can think of it as sine 2 theta plus theta. So now this is a compound angle identity, along with the sine 2 theta stuff.
Okay.
Good question. Also, the last part we can use is the easy. So which I should have talked about it before, is that if you want to find the exact value of sine of x, if you're given cosine of x, then we can use the identity, right? So it's used to swap between sine of x and cosine of x easily without losing that exact value, right? So the easiest one to use is the Pythagorean identity, but the other ones as well, they're somehow related of swapping between the sine of x and cosine of x. If you have a sine of x and you want to go to the cosine of x, then use identity train to move over to the other thing.
Why don't we just use like if it's sine of x and we want to go to cosine, if we want to change it to cosine, why don't we just say sine x plus pi over 2, minus pi over 2? Sorry.
Sine of x minus pi plus pi over 2.
Yeah.
Well, first of all, we're doing the compound angle stuff.
Yeah.
So that's kind of not used as often. Also, I don't know. Personally, I still don't memorize what sine of x is equal to and cosine of x. I don't know if it's plus pi over 2. I don't see. So I don't really prefer that method in the first place. Anyways, let's move on then to the function part. So when we have the trig function, we need to talk about some characteristics of it. We have the things like amplitude, the period, the phase shift, as well as the vertical translation. So if you have a function like this, let's say, and the amplitude is found by finding the distance from the middle, right? And the period is measured by finding the distance from the one peak to the next peak. And we also know the phase shift and the vertical translation as well. Phase shift is by finding where it would have been if there was no phase shift to the distance. And also the vertical translation is where is my midline? Like, is it going upwards or downwards?
What is the phase shift again?
Phase shift,
Horizontal translation.
horizontal translation. It's just called phase shift.
And when you write the thing down, horizontal translation is the one that you don't think it's the opposite to what.
Yeah. Also the period too. Let's say you have like sine of 2x.
Period's 2
then we
pi
think
over
of it as 2 is the period, but it's actually,
It's 1 over.
Yeah, it's 2 pi over b, which is your period.
yeah.
It's 2 pi over
2 pi over b, is it?
Yeah.
Yeah. So to note that period default is equal to pi, default of pi, 2 pi, right? Whereas the amplitude default is 1, and the phase shift and vertical shift is 0. Okay. We have two types of functions, sine and cosine. Sometimes the question kind of designates one to use for you. Otherwise, find an easy one. I think sine is a bit just more handy. It's the most solid one, the
Starts at
fundamental
0.
one. Starts at 0, 0, 2. Yes. We have some other types of functions too. We have like inverse functions, or let's talk about the tangent functions.
Oh, we need to know the
Oh.
we need to memorize the boundaries.
Yeah. So tangent function is basically tan of x. If you know that this is sine of x over cosine of x, then it kind of translates to the rational function that we talked about yesterday, right? So the rational function, we have the denominator cannot be 0, then we have a vertical asymptote, right? So we have a vertical asymptote when we have cosine of x is 0. When is cosine of x 0? We can look at the shape of the cosine of x and then we can quickly determine. Right? Cosine of x is 0 when we have pi over 2
Pi over 2.
and 3 pi over 2 and repeating, right? every pi after that. So we have to talk about the vertical asymptotes.
Period is pi.
Period is pi.
So
And
is
no, period is pi over b.
pi what?
Default is pi.
Yeah. We also have the idea of the inverse functions, such as the arc sine of x and the arc cos of x. The problem with the arc sine of x and the arc cos of x is that the sine of x and the cosine of x themselves, they're not inversible because
Yeah.
they don't pass the horizontal line test. So that's why for both arc sine and the arc cos of x, we need to limit the domain, right? So the process is that for sine of x and cosine of x, we each limit the domain. For sine of x, the domain is restricted to be between pi and negative pi, right? Because we have the shape of like this. Is it pi? I don't think so. I think it should be pi over 2, right?
Yeah, pi.
Yeah, negative pi over 2 and pi over 2. For the cosine of x, the limitation is kind of weird because we have the shape of going like this, then the limit of the domain is from 0 to pi.
Oh, it's easy to remember, okay.
I think we should be like
What are
this.
the asymptotes for tangent function?
As in vertical asymptotes are cosine of x is equal to 0.
What is it that?
So pi over 2.
Yeah, pi over 2.
What is
Okay. So then we draw the inverse. So that means that range of arc sine and arc cosine, it's going to be from negative pi over 2 to pi over 2 and 0 to pi. They're interconnected.
They're the same?
Yeah, because domain of one function is the range of the inverse of the function.
Yes.
Yeah. Oh yeah, we didn't talk about domain and range yesterday. Yeah. For inverse functions, domain of one is the range of the other one, and range of the first one is the domain of the other one. They are
Domain
swapped.
was the x and range was y. Right?
Yeah.
Okay.
For inverse functions, we just think of it as x and y flipping, right?
So for both of them, the domains would be
Negative 1 to 1.
yeah, negative 1 to 1.
Yeah.
Okay. Easy.
Right. Oh yeah. I was going to say that the functions, the strict functions, they have the range from -1 to 1. Quite an important one, because quite often we'll see some trig equations are impossible to solve because of the range problem. Lastly, let's talk about the odd and even functions of the sine and cosine. So the sine of x, which has a shape of going upwards like this and downwards like this, this is an example of an odd function, because we know that sine of x is equal to negative sine of x, negative sine of negative x. Right. If you reflect it vertically and horizontally, we come back to the same function.
Yeah.
Whereas the cosine of x, which has a shape of going upwards like this, then this is an example of an even function, because we know that cosine of x is equal to cosine of negative x. Right, I think we can move on to the next part. We can move on. Let's do equations. One more equation. So we're going to use we can solve trig equations using the identities, using the function, using various methods. One thing to note is that for the trig equations, we need to consider the coterminal arms. It's just a fancy way of saying that, for example, sine of x is equal to, let's say, 1/2, then the x can be what?
Pi over 6. Pi over 6.
5 or 6?
Yeah.
And then it can also be, okay, sorry, one more time. Like, we have to consider the coterminal arms, and we also have to consider that usually 2 cases, right?
Depends on the range.
So we have the pi over 6 and 5 pi over 6. And then we have to think about the next one, the next round. What if I add 2 pi? It's still an answer, right? So 13 pi over 6 is also the answer. And 17 pi over 6 is also the answer, and such. And so the idea of these cases are the coterminal arms.
Okay.
You don't have to know the name. But we have to understand that there are multiple and infinite answers, usually.
I remember like having questions where we had to like assign k2 pi or something.
That's the imaginary number part. What's it called?
Oh my god. Oh, isn't there like a general form?
Yeah, a general form.
When you do like modulus and argument, when you solve it, you do k plus like. I don't know how it goes, but like you have the number plus 2 pi k,
Yeah, no,
because
I
that's
remember
just
that.
a general form for every single solution.
Yeah.
Yeah, I
ever.
remember that.
Yeah. So for example, like if you have the sine, how should I say this? So we can write this as pi over 6 plus 2 pi n.
Wait, but there's more than 2 cases, so can I say usually multiple cases instead of like 2 cases?
But usually 2, right? Like usually
If
2.
it's limited to 2
You have
pi.
2 and then they're
Yeah,
repeating.
within 2 pi.
Yeah, what I mean by usually 2 cases, usually 2 cases within one rotation. If you have the case where you have more answers within one rotation, then yes, but that's why I said usually 2 cases. There could be more, but yeah, if you want, you can say usually multiple cases. Yeah. Anyways, we can do the 2 pi n as well here. Okay, so just remember that the solutions may be different, especially like when the question limits the domain for you. For example, the domain could be either from 0 to 2 pi, it could be 0 to 4 pi and such, so you have to be careful with those. Yeah, but use graph and identities. So use the graph and identities to help you solve the equations. Okay. All right. Are we done? We're done with the trigonometry part so far. Do you have any questions about the trigonometry?
That's like the easiest
Yeah.
part. Just solving for x.
I know, right? Solving for x is always the fun part.
Yeah.
Yeah,
Others are difficult.
I always forget the extra answers, and I'm just like,
Yeah,
I
I
hope
remember
they
on
give
the
me a
last test
domain.
I did the answer, but I did it stupidly wrong. I don't know why.
Wait, and then n is a element, like n is an element of w, is that the thing for like?
And is an element of
W
z,
is
z
like-
Is that
integers.
Do you have to write that?
Mm,
Oh,
sure.
usually I see that on like answer keys. And just to be clear, n is natural numbers, so like 1, 2, 3, 4, 5.
zeros.
Yeah,
Oh,
and then the
It's
w
integer.
is a whole number.
Integers are like positive
Z.
and negative.
Yeah.
And then r is rational numbers.
R is a real number.
Real numbers.
Rational
Q is
numbers are
irrational.
yeah. Q is irrational.
Okay.
All right, let's move on to the vector operations. So first off, we have the addition, which is a bit easy.
Sounds like that sounds irrational.
So addition twice. For example, we have like 2, 1 plus 3, 2 is equal to 5, 3. We just add the components together, so that's easy.
If you relate to me, just like.
And then we have the multiplication. We have two types of multiplications, right? We have the scalar multiplication. Or scalar product. And also we have the vector product. So scalar product gives out a scalar value. And what kind of meaning do they have? They usually have the meaning of the angle. Right? The angle between the two vectors can be found by using the scalar product. We have the formula for them as well, just to write that, just to note. Right? Scalar product is basically just multiply the components together, y components together, and the components together. And then we can use the second formula to find the angle between the two vectors by finding the magnitude of them.
Magnitude is just square and square root.
Yeah, let's also start with magnitude. So magnitude of the vector is kind of like the distance, right? So we take the square root of, we have them in the form booklet. Right? V1 squared plus V2 squared plus V3 squared. Okay, so that's a scalar product. The vector product gives you a vector, right? So vector has the meaning of the vector perpendicular, right, to both vectors. Okay, so it's useful when you're finding the normal vector of a plane. When you have two direction vectors, you can easily find the normal vector by doing the vector product. Another meaning that it has is by finding the magnitude of vector product, we get the area of a parallelogram. Which is a bit less useful, but sometimes you'll see questions like that. Okay, and then we also know that area of parallelogram of, let's say, V and W, so we can find the area of is magnitude of the vector product, and then we can also cut it in half, right? And then we can try to find the area of a triangle by finding the half of the area of the
Wait,
parallelogram.
when it says the area of parallelogram, how would you decide if the vectors are going infinitely? Like,
Vectors don't go infinitely.
oh yeah, sorry.
Yeah, vector has a magnitude. Vector has a distance.
Your V and W is the vectors. It
Yeah.
would find the area of that parallelogram.
Yeah. All right. Addition, scalar product, and the vector product.
Why is this parallelogram formula useful?
Wait,
Was it
asks-
useful?
Huh?
It asks sometimes
the
when
scalar
IB decides to
product
become
is
meaner than it already is.
radian.
It doesn't matter. But yeah, angle and radians, sure.
Yeah, radians is easier.
Yeah, radians are
Easier
easier.
because you can do the 1, 2, 3, 1, 2, 3.
Wait, what's the formula for scalar? Like,
The vector product is slightly more difficult to find, right? Scalar product is easy. You just plug in the values and you get a number. The vector product, we have this weird formula. Once again, you can use them if you want. And also, they also give you the angle between the two vectors, but just finding the vector product is a bit more difficult than finding the scalar product. So I think it's inefficient to use the vector product to find the angle between the two vectors. The formula tells you that method, but I like to use my methods for the vector product. So let's just go through them. Let's say we have the vector v is equal to 1, 2, 3, and w is equal to, let's say, negative 1, 0, 1. Then
No, I saw like the organic chemistry.
if I want to do v vector product w, then what I do is I'm going to write down the 1, 2, 3, negative 1, 0, and then I, j, k, and then I repeat myself. And then what I do is I multiply the diagonals together, and then I'll add them together. So I get like 0k minus 3j plus 2i, and then I do the same thing, but this time I go the other way, and then this time I'm going to do minus. So minus 3i, so minus 0i, and then plus, was it? Plus j, plus 1j, and then plus 2k. So I say that, and then I collect like terms. So it's 2i minus 2j plus 2k. So I know that it's going to be 2, negative 2, and 2. But that's, I think for me, it just works better than using the regular formula. If you don't want to have another method, you can use the formula booklet and suffer in your own cost. Personal opinion. Anyways, Right, any questions about the vector operations and the ideas of vectors? Once again, vector has a magnitude, it has a direction, okay? But then we're not happy just with vectors, right? So we need to go a bit further. So let's go with lines and planes. So equations of lines and planes. So for both, we have 3 versions, right? 3 versions. Further proving the triforce of the math. For the lines, we have the vector equation for the line, we have the parametric, and then we also have the, what is the last one? Cartesian?
Yeah.
Knowing how to go from one to the other is important, but I think the line equation is pretty simple, so I'm not going to mention too much about it. One thing to note is that the line is formed of 2 components, right? It's component of a position vector, and then we also have the direction vector.
All of it is on the booklet too.
Yeah, all of them are on the booklet, so it's easy to use.
Does SL not need to do vectors?
No,
No,
they have no vectors whatsoever.
it's actually unfair.
Because the use of vector only appears when we do further calculus, right? So if you don't take the IB route, you first learn about the vector when you go to like second year mathematics.
God.
Yes.
Anyways, so that's for the line equation. We have 3 types. For the planes, it's a bit different. So let's look at the formula booklets. So we have the vector equation, and then we have the normal. So we have 3 forms, but essentially we just have 2, right?
You only use one.
Yeah, we have
You only
the
use
vector equation and the Cartesian equation. So for these ones, we have 2 versions, right? We have one equation will give the position vector, followed by 2 direction vectors. And then the Cartesian one gives you the position vector plus a normal vector. Once again, the normal vector, normal means perpendicular in 3D basically. You find the normal vector of a plane by finding the vector product of 2 direction vectors. Basically, the 2 direction vectors, think of them as vectors that are on the plane, and the normal vector, think of it as where the plane is facing. Like if you imagine yourself as a plane and you're looking forward, you're looking straight, and that's a normal vector, right? And your arms and your legs will be the 2 direction vectors. I should use that in my class. I think that's a perfect one. Anyway, so we have these types of equations of lines and planes. One thing to note is that when we say that it's something, a point is on the line or on the plane, we mean this is equivalent of saying that the equation is true. Right? So we can plug in the value into the equation to say that, hey, it is indeed on the plane or is indeed on the line when the equation, the left hand side and right hand side, are true. Okay?
For the Cartesian equation, it's A, B, and C are the components of the normal vector, right?
Yeah.
And
Okay.
X,
Yeah.
Y, Z is
Let's go through them.
What do you mean by the last thing you just said?
The equation. All right. So, for example, like there was a question today when we discussed, right? I give you a point and say, hey, is this point on the line?
Oh, just
Then
equate each
you
other.
put it into the equation. Right? Let's talk about the Cartesian vector, the plane equation a bit more. So we know that the plane equation goes as r is equal to a plus, what is it?
R dot.
Lambda b plus mu c. Right? So we have the parameter mu and c, and we have the two direction vectors b, c, and the position vector of a. And then what we do is we know that the normal vector is going to be the b cross c, right?
Yeah.
So we know that after you find a normal vector, if you multiply both sides, or if you find a scalar product with normal vector on both sides, you get r dot n, and it's equal to a plus lambda b plus mu c, scalar product with n, right? And because we know that the scalar product of two perpendicular vectors are zero. And because we know that b normal vector is perpendicular to both b and c, so we know that it's going to be 0 for all the terms. Basically, you have a dot n plus 0 plus 0. Right?
Why is it 0 again?
Because when you find the scalar product of two perpendicular vectors, it means that the cosine theta is going to be
Oh yeah. 0.
perpendicular means cosine of pi over 2, which means it's 0.
0.
Yeah. So that's how we know that. And then the left-hand side opened up, basically, is the r is x, y, z. And the normal vector, again, now we use a, b, c. So then we do ax plus by plus cz is equal to d. Okay, so r here is, we usually use x, y, z. And the n, we usually use component a, b, c for the normal vector.
I only use Cartesian.
It's pretty normal.
Cartesian easier. Like these ones, you have to do so much more steps. If you
But
just-
there may be a chance that you get a question where they give you the vector equation of a plane, and
Well,
then you
then
have to
I'll
find the
switch it to-
Cartesian plane. So then you have to use that transition. Right? Anyways,
We can go back from Cartesian to vector, right?
But why would you?
For some reason. I don't know.
yeah. I mean, you probably could.
You have to define new vectors though. Like new.
Let's not talk about that.
Yeah, exactly.
All right, let's talk about the last part: interactions. Interactions of planes and lines. So the first easiest interaction that we have is the angle. Right? So when you have the angle between planes and lines, well, we just talked about angles. So how do you find the angles? By finding the scalar product. Right? So what we have to do is instead of trying to find the angle between a line and a plane, you try to find the angle between a line between two vectors. Right? Whether they're the direction vectors or the normal vector. Right? So if you have a line and a line, then we're going to compare the angle between two direction vectors. If it's a line and a plane, then we need to find one way to do it is we need to find the projection vector under the line on the plane. Or we can think of it as, you find the angle between the direction vector of the line and the normal vector of the plane, and then we do what is that word called? I forget. The 90 minus that angle, or pi over 2 minus that angle.
You can also switch it to sine, just straight up.
Yeah, you can do that too. If you have the angle between the two planes, then we find the angle between the two normal vectors. And then that helps you find the angle between the two planes as well. Another type of interactions that two planes and lines can have is the point of intersection, or intersection, let's call it. Intersection means that you're solving equation, solving systems of equations. So if you're trying to find the intersection between the two lines, then the two lines are, so basically you have the parameters, and both parameters have to be true, right? So then you put the parameters into systems of equations, and then you solve the parameters. If you are trying to find the intersection between a line and a plane, that's kind of different. Basically what you do is you substitute the parametric equation of a line, and you put it to the Cartesian equation of a plane. You put it inside, and then now you suddenly have just one variable equation. If you're trying to find the intersection between the planes, then if it's two planes, then you try to find the line of intersection. Okay. To find a line intersection, you need to find the position vector and the direction vector. So you first randomly choose one position vector, and then you find a direction vector, finding the vector product of two normal vectors. If you have three planes that are intersecting, then we can do a 3x3 linear algebra to solve that problem too. And based on the results of the 3x3 linear algebra, sometimes we'll have a one point of intersection, or no points of intersections, or line of intersection as well, possible. Okay. Lastly, we could have what's the last one? Distance. So for the distance, what you're going to do, you're going to find a point. Find a point find the shortest point, the closest point, find two closest points on lines and planes, and then you find the distance, right? So to find the closest point, basically what you're doing is you're finding the perpendicular or the normal vector between the two lines, and that's always going to give you the closest point. Okay. So this is for the skew lines, or a line over a plane, or such. Okay. The skew is usually the hardest one, in my opinion. Anyways. No. For me, when I was learning this topic about vectors, it was hard. But now that I think about it, it's not too bad. Right? There are some harder ones, in my opinion. So hopefully we had some good time here. Any questions about the topic 3?
What was the when you solved your system of equation for the plane, for like 3 planes?
Yeah.
What when you
What are the cases?
What are the cases?
Right. So basically, when you have a row of 3x3 matrix, let's say we have 0, 0, 0, and then 0, 0, 1, and then let's say 2. Let's say I have a case like that, then this is good. Right? We have a point of intersection.
So that means all 3 planes are meeting
at a single point. Right? Or sometimes you have 0, 0, 1, 0, 0, 0, and then 0. Then this is fine. The problem is that why this happens is that the 2 rows were identical. That's why this happened, right? Then it's not a problem, but we just have insufficient evidence to pinpoint one point, which means in turn we have a line of intersection. So we say that this is a line of intersection.
It's just one row though, right?
Yeah, one of the rows. If you have if you have 2 rows of 0, 0, all zeros, then it means that we have a plane of intersection, which means that we just have 3 of the same planes, basically.
Wait, is it 3 or 2 same plane and 1 line? Would it be
2 same plane and 1 line, also possible. Another case is where we have 0, 0, 0, and let's say 2. then this is no point of intersection.
Well, it has random intersection. It can be like three line, like two of them are like this, and then
Yeah.
last one.
Or
is,
no, like one point of intersection.
How do we know
Can't really
what
find
actually-
it.
Do
Sorry?
we find it, or do we need to find the nature of the interaction?
No.
Okay.
What they'll tell you is like, the question will ask you explain what your answer, and you'll say there's no unique point of intersection, and that's it.
For
Kinda.
what?
Yeah.
Okay. Any other questions? Okay. Hopefully we'll be seeing some applications of these in the test setting. So we'll go through them in our past paper solutions session. Okay. 5-5, 5-5.